Molecular clouds. So, the reason I chose this topic was because I heard molecular, and I'm a chemist, so naturally I was interested. And I've also been very curious about how elements and molecules are formed out in space because the conditions are crazy different than what they are down here on Earth. So, we're going to start with interstellar medium. And interstellar medium is everything in between the stars. So that could be gas, either in its ionized form, atomic form, molecular form, or dust and waves and things of that nature. So interstellar medium is very sparse, right? Not dense at all, practically a vacuum. It's also really cold. So what do I mean by really cold? About 100 Kelvin, which in American temperature would be negative 280 degrees. So my cat also thinks that's very cold. So when the interstellar medium gets a little bit more dense, forms nebula. Now, this is from the textbook, it's not my definition. Nebula is a general term used for any fuzzy patch on the sky, whether it's light or dark. So, nebula are what you think of when you think of a galaxy pattern, right? So, they're these really beautiful clouds. Nebula actually means cloud in Latin, so aptly named. This is the Pac Man Nebula. This is the Ghost Head Nebula. I think I just chose ones that had funny names. Tarantula Nebula, but they're also super gorgeous. Twin Jet Nebula, that one's fun. And Lagoon Nebula. So this brings me to my next point, or the next most dense thing in what I'm talking about. So you have those dark spots there, right? And we were talking about nebula, light or dark, so these are the dark ones. And there's a little close-up of the Lagoon Nebula. So why is it dark, right? These are called dark dust clouds, despite the fact that they are made of mostly gas, hydrogen gas, actually. And the reason that they're so dark is because visible light cannot pass through them, right? They're so dense that the light is not able to pass through them, so it blocks the light that is being emitted from behind it. And I mentioned that they're made of hydrogen, mostly hydrogen, atomic hydrogen, right? Just the atom form. So how do we know that, right? We said before in a previous video that we know what elements are out in space based on their emission spectra, right? So the excited electron falls back down to the ground state, releases a photon. It's not releasing visible light. How do we see it? Well, luckily, we have radio waves. So, inside of a hydrogen atom, there's the proton and the electron. When they are spinning in the same direction, that's a higher energy state called parallel spins. Anti-parallel spins are lower, right? So instead of going in the same direction, they're going in opposite directions, right? And that is clumpier for the atom, requires less energy. So when it goes from the high energy state to the low energy state, all it's doing is flipping the spin of the electron, but that releases a photon. So that photon is not as high energy as what we see when we have the emission spectra. If you take a look in the middle here, the visible spectrum, right in the middle, if you go more to the left, gamma rays, X-rays, ultraviolet, those wavelengths are much shorter. On the right, over here, radio waves are super long, lower energy, right? So because we are releasing less energy, the wavelength is going to be longer, and that wavelength being super long, 21 centimeters, it's actually able to travel through the interstellar medium without being interrupted. So we could see them nice and clear. And the Horsehead Nebula is probably the most famous dark dust cloud. We see it a lot, right? So when these dark dust clouds get a little bit denser, they form what are called molecular clouds. Now, molecular clouds are more dense and they're also much colder. So a dark dust cloud is in the tens of Kelvin, which I guess is somewhere between 100 and 20, because molecular clouds are between 20 and 10 degrees Kelvin, which is incredibly cold, considering 0 Kelvin is when the motion inside of an atom stops. So, molecular clouds, important thing here. We were talking about atomic hydrogen before, the spin changing. The problem with molecular clouds, instead of having atomic hydrogen, they have molecular hydrogen. Now, why is that a problem? Molecular hydrogen is really symmetric, right? So symmetric that it doesn't absorb or release any waves whatsoever. It's just super symmetric. So because molecular hydrogen doesn't absorb or emit any waves, how are we looking at it? Right? Before we were saying that the atomic hydrogen was already hard enough to see, but we were able to use the radio waves that it emits. Now we don't even have those radio waves. So how do we know what's inside a molecular cloud? Luckily, we have other molecules in there, right? So carbon dioxide, you may look at it and say, that's pretty symmetric also. But because there's a carbon on one side and an oxygen on the other side, the electrons aren't shared equally, right? So the oxygen is pulling electron density away from the carbon, making the carbon have a positive charge and the oxygen side have a negative charge. So, lucky for us, that is able to absorb and emit waves. Right, so here in this picture, what we're seeing is the density of carbon monoxide molecules. And these are called tracers, right? So there's carbon monoxide, there's formaldehyde, there's apparently the molecule that is in vodka. So they use these molecules, the presence of those molecules, to determine how much molecular hydrogen is present. Right, and here we have a contour map, right? So much like a, contour map here on Earth where the lines are closer together, that means you have a higher concentration. And on the left here, we see what it looks like just to the naked eye, right? The V on the bottom there with the wavelengths means the visual spectrum. So on the left is what we would see if we're just looking at it with our eye. Kind of looks like there's something missing there, right? Like just a dark patch in space. And there is something missing there. It's called visible light. Luckily, like we said, we're able to use the wavelengths, the radio waves emitted by other molecular compounds to see what's there. So why are molecules only found in these super dense interstellar clouds called molecular clouds? Well, like we said before, gamma rays, X-rays, ultraviolet rays, they have lots and lots of energy, which would essentially destroy any molecules that are trying to be formed. But the dust clouds, they don't let those pass through. All they allow to pass through are the radio waves. And those radio waves are nice and easy. They're not going to hurt any of the molecules. So essentially the dust is protecting them, right? It's protecting the molecules from all the crazy, harsh interstellar conditions. Another reason that the dust helps the molecules form is because when you have things bonding, right? When you're forming a bond, you're releasing energy, right? If we remember our acronym BARF, breaking a bond absorbs energy, right? You put energy in. Forming a bond releases energy. So when these bonds are forming to form molecules, they have to release some energy. Without the dust there, that energy would just be building up, making it hotter, and then that would destroy the molecule as well. So the dust kind of dissipates some of the heat and makes the conditions favorable for molecules to form. So I'm going to end on this very pretty picture with this extremely adorable caption from NASA. So young stars in their baby blanket of dust. How cute does that sound? They're like babies. And the reason I wanted to mention this was because A, it's super cute, and B, these dark dust clouds, these molecular clouds, these nebula, these are how stars are born. And sometimes the molecular clouds are actually called stellar nurseries, which is really cute because I just love thinking of babies. Okay, thank you for watching.